In this video, we'll take a look at the first of a few very specific applications that result in linear systems. And this application has to do with what we're going to call a general network. Now, what is a network? So, a network is a series or set, not series like infinite series, but just a series of what we call nodes or junctions, or sometimes more generally vertices, right? Connected by either directed edges or arcs, right? And right, so that's what we will use as our definition of a network, right? So what do they look like, and what do you use them for? Well, like for instance, here's a very simple network. I'll have one node, and let's say I have a couple arcs there and one arc there, and let's say they're directed in this way, right? So, for instance, this could be like an intersection of three roads, right? And these two are one-way roads leading into this junction, and then this one is a single one-way road heading out of the junction, right? And you could have any sort of information flowing along the or through this network, going along the arcs and passing through the different junctions. So for instance, like an underground sewage network, you would have sewage flowing through all those pipes. So the pipes, would be like your directed arcs, right? And then when a pipe branches from maybe 1 to 2 or so forth, then every time it branches, the branching would occur at a node. Another example might be a computer network where you have different maybe servers connected, and then you have information flowing from one server to the next, right? So there are lots of things that you can use this sort of structure to model. Now, what's the general problem? Well, what we will know in our networks is we will know, for instance, how much of this quantity is flowing along some of the arcs, and then we might have an unknown amount of the quantity flowing along the other arcs. And our goal is to try to solve the network by figuring out what are these unknowns, right? And there is one guiding principle that allows us to turn problems like this into a set of algebraic equations. And here is the principle, right? And it's based on the work of Kirchhoff or Kirchhoff. I've heard people refer to him both ways. And this is his principle. The sum of the inflow, so the sum of everything that's flowing into a node, so the sum of the inflow at each node in your network must equal the sum of the outflow, right? A very, very simple principle. And in like a physical sense, this is one version of what's referred to like a conservation law, where nothing is created or destroyed. It's just flowing from one area in the network to another area. So for instance, going back to the example of sewage, it just means that the pipes in that system are leak free. They have no leaks, so there's nothing leaving the system. It's just flowing throughout the system from one point to the next, and it's flowing along these directed arcs. So in our little example here, this picture now equates or is equivalent to this algebraic equation: x1 plus x2 is equal to 20. The x1 and the x2, those are inflows because the arrows are pointing towards the node. So the sum of what's flowing in is x1 plus x2, and there's only one arc pointing away from this node, and it has a value of 20. So this here is the sum of the inflow, right? And this is the sum of the outflow, and they have to be equal because of this principle. All right, and that's it. It's a really simple idea, but it's amazing how many things you can boil down to a network like this and then apply this principle, right? So the best way for us to see how it works is to do an example. So here is my example. I'll use a system that's not terribly large, but also I don't want it to be too small so that you don't really get a sense of the process. And let's say I have a nice diamond shape there. And what I'm going to do, I'm going to have the arrows going counterclockwise like this, right? And then I'm going to have some other arcs, basically north, south, east, west. So let's say I have 20 going in there. And just to make it nice and symmetric, let's say we have 20 going out there. And then for this one, let's say I have 10 going in to this node. And then again, for make it nice and symmetrical, it doesn't have to be, but we have 10 going out. And what we don't know is how much of this quantity is actually flowing along these four. So let's call it x1, x2, x3, and x4, right? And the first thing that we want to do, our instruction would be like, solve the following network, or what is the general solution of the following network. So that's what we're going to do first. Solve the network. Right. So our first step will be to apply this principle of Kirchhoff at each node. So as to make it clear what we're doing, let's go ahead and label the node. So I can say at this node this is happening, at this node this is happening. So I'm just going to label them 1, 2, 3, 4. Now we can actually set up a nice table that reflects this, right? So let's have the first column represent the node. So there are 4 of them. And then let's say our second column will represent the sum of the inflow. And then the third column will represent the sum of the outflow. Okay, and let's see what happens. So at node 1, there are 2 arrows pointing towards this node for a total of x2 plus 20. And then there's only 1 arrow pointing away from node 1, and that's the unknown value x1. At node 2, let's see, there are 2 pointing away, but 1 pointing towards, so the inflow is simply x4, and the outflow is x2 plus x1. And then at node 3, we have x3 going in, and then the sum of x4 and 20 going out. So x4 plus 20. And then finally at node 4, we have two arrows pointing towards it. X1 plus 10 is the sum of the inflow at node 4. Oh, I said 4 and almost, well, not almost, I wrote it 4, but that needs to be a 10. And then finally, the sum of the outflow at node 4 is X3. All right. So now that we've done that, we don't even need to look at the picture anymore. Like, well, where did it go? Right? It's like it's real. Like what we're doing here again, and I want to emphasize it. It's the process of taking something physical and slowly making it more abstract. Right? So let's continue that abstraction. So now the principle says so. X2 plus 20 is equal to X1. X4 is equal to X2 plus 10. X3 is equal to X4 plus 20. And then X1 plus 10 is equal to X3. That's that conservation law, that whatever goes in comes out, right? So this is not technically in a standard form yet because we have variables on both sides, we have constants on opposite sides. So let's make this more systematic. So the first equation in a more standard form would be x1. So yeah, what I could do is I could take over the x2 and make it minus x2, and then that's equal to 20. And then the next equation, if I move the x2 to the left, I'll have negative x2, and then plus x4, and then that's 10. And then the next one, move over the x4, so I'll have x3 plus x4 is equal to 20. And then finally, what I can do here is move over the x3, move over the 10, and I get this, x1 minus x3 is equal to 10, right? And then we can make it even more abstract because we know that, the variables are irrelevant. So let's turn this into an augmented system, and then we will put it in one of our echelon forms, right? Because that's kind of what we our goal for anything that ends up being a linear system. And if what we're doing is solving, we're gonna end up using our echelon forms. So let's write all of these values down. There's a lot to write. And then the third row is 0, 0, 1, negative 1, 20. And then the fourth row, 1, 0, negative 1, 0, negative, oh yeah, this should be a negative 10, right? Negative 10. Okay, so now let's see, in terms of putting it in at least REF, we have our pivot of 1, so what we have to do is, that's our pivot, we're going to eliminate the 1 in the first column, fourth row. So I need to use this operation, negative R1 plus R4, right? And let's see. So let me write it column by column. 1, 0, 0, 0, and then negative 1, negative 1, 0, 1, and then 0, 0, 1, negative 1, and 0, 1, negative 1, 0. And then the column with the constants, now we have 20, 10, 20, and now this constant becomes negative 30 because I'm taking the negative 20 and then adding it to negative 10. All right, so the first column is okay. Now I need to make this a 1. Right? In order to call it an echelon form, I need to make this a 1. So I need to take negative 1 times row 2. Now I'll, just to keep entertaining myself, I'll write it by rows now. So this becomes 0, 1, 0, -1, -10, and then 0, 0, 1, -1, 20, and 0, 1, -1, 0, -30. Okay, so there we go. And we have, just like we had before, we just have to eliminate this 1 in row 4. So with this as my pivot, I can use a very similar operation here and do the negative of row 2, add it to row 4, and this is what we will get. So we're going to end up with, maybe I'll go rows this time. 1, -1, 0, 0, 20, 0, 1, 0, -1, -10, 0, 0, 1, -1, 20. And then now the fourth row will change. We end up getting a 0, 0, -1, 1, -20. Right? Now if you look closely, look right now in the current form, look at rows 3 and rows 3 and 4. Do you realize that the coefficients in row 3 are the exact opposite of the coefficients in row 4? That tells me now when I use this as my, so this is my next pivot, when I eliminate the -1, I am going to eliminate not just the -1, but everything in that row. So I'm going to have my row of zeros at the bottom there, right? So let's do that. So we're going to end up with, so I just have to take row 3 and add it to row 4. And 1, -1, 0, 0, 20, 0, 1, 0, -1, -10, 0, 0, 1, -1, 20, and then I'll have my row of zeros right there. And one thing too, like, you know, when you have so many entries to keep track of, once you realize that you've eliminated an entire row, you can literally stop writing it because it holds no relevant information. All this row is telling us now is that 0 is equal to 0. You know, so rows like this, you know, they're redundant. They're not telling us anything new, right? And so let's see. So in this is an REF, right? So we've now gotten it in REF, and it's actually fairly close to being an RREF because the only thing preventing it from being an RREF is the fact that here is one pivot that has a -1 above it, right? All the in all the other columns with a pivot, the other entries are 0, right? So if we just eliminated this, then we could say it's an RREF, and that will make it even a little easier to write down the solution. So going back and using this as my pivot, let's eliminate the -1 that's above it. So if I take our row 2 and add it to row 1, this becomes my new augmented system. And again, I'm not even going to write the zeros. I don't need to at this point. So there is the first column. Second column is 0, 1, 0. Third column, again, I'm not writing the bottom row, 0, 0, 1. And then we have -1, -1, -1, and then 10, -10, and 20, right? So this is now an RREF. And remember, we have 4 variables, but only 3 pivots. So what this means is the column that correspond, or the variable, sorry, that corresponds to this column is free. And that happens to be x4, right? So let's write this. So this means we have to use our parametric solution. So let x4 be equal to t, any real number. So the bottom equation is telling me that x3 minus t is equal to 20. So therefore x3 is t plus 20. Right? And then x2 minus t is equal to negative 10. So therefore x2 is t minus 10. And then finally x1 minus t, that's equal to 10. So therefore x1 is t plus 10. So here is the general solution, or our parametric solution for this network. Right? So here's our solution set. So let's see, x1 is t plus 10, x2 is t minus 10, x3 is t plus 20, and then my free variable t is x4. And again, t can be any real number. All right, so that's it as far as the solution. Part B. Well, what could we do with the solution? Well, just to illustrate the idea, we did this previously, where we identified, even though we realized that the system has infinitely many solutions, we could write down some specific ones. So here is the, part B. Find the flow when x4 is equal to 100, let's say, right? So if x4 is 100, then it means my t is 100, right? So this implies t is equal to 100, and then I simply need to plug 100 into this, and then I can find that unknown flow, right? So what do we have? So 100 plus 10, so that's 110. 100 minus 10, so that's 90. 100 plus 20 is 120, and then 100 is in that fourth position, right? So this is the flow at well, I guess you could say like at t equals 100 if t represents time, but in this case, I don't really think it would be time. It would be whatever is flowing along that arc that's labeled x4. So if there's 100 flowing along that arc, then there has to be these amounts flowing along x1, x2, x3. All right, and that's our general network. Simple principle. We can turn it into a linear system, and now we have all the tools to solve and interpret the solution. Right? Hope you found that interesting, and I'll see you in the next video.